My love for you is like the square root of 2. That's a nerdy way to flirt, oh buddy, it's true. Cause if you write that number straight out to the umpteenth decimal place, you notice that it don't repeat and it never terminates. My affection's never ending, every day is new. Now my love is like the square root of 2. Written as a decimal, my love is like the square root of 2.
Hey, 8th grade! That intro there was to kick off the start of our next unit, which is over radical functions. It's going to be fun and exciting, so let's get to work. So we had a brief intro to the topic of nth roots. The last time I saw you in class, we went through and we made that index card, if you remember, of the perfect squares, cubes, perfect fourths, perfect fifths, etc. So I just want to recap a little bit of what we talked about there. So try to follow my logic here. We know since 7 squared is equal to 49, that means 7 is a square root of 49. Okay, and similarly, since 4 cubed is equal to 64, that means 4 is a cubed root of 64. And then we also started talking about perfect fourths and perfect fifths. So 5 to the fourth, for instance, is 625. Therefore, 625 is a perfect fourth, and 5, we would call that a fourth root of 625. And similarly, 2 to the fifth is equal to 32. 32, therefore, is a perfect fifth, and 2 is a fifth root of 32. So this is what I mean by nth roots. Okay, the basic definition of an nth root is this. If you have some number a, and you take it to the nth power, that would be equal to b. Okay, then if you take the nth root of b, that reverts you back to a. Okay, so for instance, we took 2 to the fifth, set that equal to 32. Well, the fifth root of 32 was equal to 2. Okay, so this is the definition here of an nth root. I want to talk about a little bit of vocabulary here. So the n value in this notation here, the n value is what's referred to as the index. That's the little small number that's sitting there sort of in the crescent of the radical sign. And the number underneath the radical, or the variable underneath, it's what's called the radicand, okay, the part underneath the radical. So the first thing I want to talk about with nth roots are the fact that some numbers have more than one real nth root. For example, we know that 64 actually has 2 square roots. That would be 8 and negative 8. If you guys remember, when you solve equations and you square root both sides, I harp on you for putting your plus and minus signs in front of your answers. That's because in this case, 8 squared gives you 64, and negative 8 squared also gives you 64. Okay, but when you're using the radical sign itself, okay, when I give you a problem like what is the square root of 64, it's a little bit different. Okay, when there is more than one real root and n is even, so for all square roots, okay, your n value would be 2, so n would be even. The non-negative root we have, in this case 8, is what's called the principal root. And when you see something like this, radical 64, that actually means that the only answer that you need to give is the principal root. So in this case, that would be just 8. Okay, it's a little bit different than actually solving an equation and taking the square root of both sides. Okay, in that case, you'd put the plus or minus. But when you just see something like radical 64, it is defined as simply 8. So for example, if I gave you a problem and it just said simplify radical 25, your only answer would be 5, because this, again, symbol means give the principal square root, which is the non-negative. Okay? If I put a negative sign in front of the radical, that means give the opposite of the principal root. So the opposite of positive 5 would be negative 5. So this is where you'd use the negative 5. Finally, if I put the plus or minus sign in front of the radical, then that means you'd put plus or minus 5 to indicate both square roots, just like when you solve a quadratic equation. Okay, so down here in these first few examples, we're just going to practice simplifying nth roots of numbers here. First example, I have the fourth root of 16. And so if you're looking at your index card, you see that 16 is actually one of your perfect fourths. 16 is 2 to the fourth power. And so the fourth root of 2 to the fourth power would just be 2. Okay, next, number 2, we have the fourth root of negative 16. Well, just like square roots, you know you can't take the square root of a negative number. The same is true of all even roots, so the fourth root would be the same. We cannot take an even root of a negative power because you can't take a number times itself an even number of times to get a negative. So we would actually say in this case that there is no real fourth root. There is an imaginary root for this, but we're not going to get into how to do imaginaries of fourth roots. You guys know how to do imaginaries of square roots, so if this were a square root, we could simplify that, but we're not going to get into imaginaries for anything higher than a square root. So just no real fourth root for number 2. Number 3, we have the cubed root of negative 125. You can take the odd root of a negative number. That is allowed. Okay, if you think about it, 125 is really 5 cubed, and so to get a negative 125, you would have to take the number negative 5 and cube it. Okay, so this number actually does exist. The cubed root of negative 25 is just negative 5. And then finally, number 4, we know how to simplify radical 20. 20 is not a perfect square, but I know that 4 goes into 20, and 4 is a perfect square. So that becomes radical 4 times radical 5, which gives you 2 radical 5. Okay, so make sure you remember this process, how to simplify radicals. We'll be using a similar process to simplify some higher degree roots in the lessons to come in this chapter. Okay, so a summary of nth roots up here in this table that I want you to be familiar with is anytime I'm giving you a problem like this, the nth root of a. If n is even, so if you have a square root, a fourth root, a sixth root, okay, and your radicand, your a value is positive, then you're always going to have 2 real nth roots for your answer. Okay, there are always 2 real nth roots, but you're only going to list the principal, okay, the positive, unless I put a negative sign or a plus or minus in front of the radical. Okay, so there are 2 real nth roots anytime you have a positive and n is even, but you only have to list the principal. Okay. If n is odd, though, there's only 1 real nth root. Okay, so if your index is odd, there's only 1 real root. When your radicand is equal to 0, there's only 1 real nth root when n is even. Okay, the square root of 0 is 0, the fourth root of 0 is 0. So anytime you're taking a root of 0, you always get 0. And same thing when n is odd. Doesn't matter if it's a fourth root, a fifth root, etc. The root of any 0 would still be 0. When your radicand is negative, okay, when a is less than 0, we know you can't take an even root of a negative, so there are 0 real nth roots. Okay, that's when you start getting into imaginaries. But when you have an odd index, you can take the nth root of a negative number. We did the cubed root of negative 125 on example 3. Okay, so there is 1 real nth root when your index is odd. Okay, let's move on to some examples now with variables, how to simplify radicals with variables. Number 5 here, we have plus or minus, so that just means we're going to put plus or minus in our answer and list both roots. Plus or minus radical 16y to the 4th. Okay, well, we know from working with radicals in the past that we can split up the number part and the variable part as long as we put them both underneath radicals. So this would be the same thing as plus or minus radical 16 times plus or minus radical y to the 4th. Okay? Well, we know the square root of 16. Okay? The square root of 16 is simply 4. So this would be plus or minus 4 times the square root of y to the 4th would just be the square root of y squared squared, or simply y squared. Okay? Y squared times itself gives you y to the 4th, so this answer would be plus or minus 4y squared. Okay, the reason I'm writing it this way is because I want you to see it written as a power of a power and start getting used to those exponent properties again, because exponents are going to come back up later in this unit, properties of exponents. So that's the reason why I'm writing some of these in that notation. For instance, number 6 I'm going to write in that notation. We have the square root of a binomial here. We have, first of all, a negative square root. So we want to make our final answer negative here. So we have the negative square root of x squared minus 6 to the 8th power. Well, if you think about it, x squared minus 6 to the 8th power would be the same thing as x squared minus 6 to the 4th power taken to the 2nd power. Okay, go ahead and take a look at that for a second. X squared minus 6 to the 4th power, if I take that entire thing here in red and square it, I multiply my exponents together and I get to the 8th power. Okay, so if I take a square root of something squared, we know that a square root of something squared cancels out the 2 and the square root sign. So really, the square root of this binomial, x squared minus 6 to the 8th power, just gives you x squared minus 6 to the 4th power. And again, we want to make that a negative. Okay, so if you think about undoing your exponent properties for some of these, that allows you to figure out what the final answer is supposed to be. Okay, you need to recognize that something to the 8th power can be rewritten as something to the 4th power squared. Okay, and therefore the square root of that would just be this expression to the 4th power. Number 7, we have the 5th root of 243, a to the 20th, b to the 25th. So I'm going to split that up into the 5th root of 243 times the 5th root of a to the 20th times the 5th root of b to the 25th. The 5th root of 243, if you're looking at that index card that we made, we see 243 is on our list of perfect fifths. It is in fact 3 to the 5th power, so that would just be 3. Again, we're not putting the negative sign because this symbol here means just list the principal root. The 5th root of a to the 20th would be the same thing as the 5th root of a to the 4th power taken to the 5th power. Okay, if you take a to the 4th and then take it to the 5th, 4 times 5 is 20. And so that means that the 5th root of a to the 20 is simply a to the 4th. Okay, same thing with the 5th root of b to the 25th power. Okay, b to the 25th power can be rewritten as b to the 5th to the 5th. Okay, and so that would just become b to the 5th. Okay, so your final answer here would simply be 3, a to the 4th, b to the 5th. Okay, finally number 8, we have the square root of negative 16, x to the 4th, y to the 8th. I'll split that up again. We can't take the square root of a negative, but we do know how to work with imaginaries. So anytime you're doing a square root of a negative, I want you to write that in the imaginary form. This would be this would be 4i. Okay, the square root of x to the 4th would simply be the square root of x squared squared, or x squared. And then the square root of y to the 8th would be the square root of y to the 4th squared, or simply y to the 4th. And so your final answer here, you get 4i x squared y to the 4th. Okay, so the last thing I want to talk about this section, this is where the fun really begins, is what happens when you take an even root of an even power. So let's say we have the square root of x squared. Okay, so the square root would be index 2. Okay, so what happens when you take an even root of an even power, x squared? Does that give you, in this case, x? Well, let's suppose x equals 5. Okay, if x equals 5, then the square root of x squared would be the square root of 5 squared. Okay, well, we all know that 5 squared is 25, so that would be just the square root of 25. Radical 25 is equivalent to 5. and x was originally equal to 5. So in this case, it holds true that the square root of x squared is in fact equal to x. That's a true statement. But what if x is equal to negative 5? Well, in this case, if you take the square root of x squared, that would be the same thing as the square root of negative 5 squared. Negative 5 squared is positive 25, so that gives you radical 25, which is equivalent to 5. But x was not originally equal to 5. X was actually equal to negative 5. So in this case, radical x squared is not equal to x. Okay, so this up here would not be a true statement when x is equal to negative 5. But it is equal to the absolute value of x. Okay, the absolute value of negative 5 is 5. Okay, so you may be asking yourself, okay, why in the world are we worried about this? Well, anytime you're taking radicals of variables, and specifically you're taking even powers of, or even indexes of even powers, okay, even nth roots of even powers, you need to be careful and look for the use of absolute value signs. For any negative real number a, the nth root of a to the nth will be equal to the absolute value of a whenever n is even. Okay, so let me put that in a little bit simpler terms. When you find an even root of an even power, and also the result has to be an odd power. So even root of an even power and the result is an odd power, even, even, odd, you have to use absolute value around the variable for your answer. Okay, based on these two examples we did up here, okay, we discovered that when x was negative 5, the square root of x squared wasn't just x, it was the absolute value of x. So therefore, when you have variables and this scenario, even, even, odd, you have to use absolute value bars. So let me show you what that looks like down here in these examples, because I'm sure some of you are lost on that right now. I have the fourth root of y to the fourth. So this should be your red flag right here. You have an even root of an even power. Okay, so when we take the fourth root of something to the fourth, we just get that base right there. We just get the y. So normally we would say, okay, y is our answer. But because we had an even root of an even power and our resulting answer is odd power, this is y to the first, we have to use absolute value bars around it. So the answer to this problem is really the absolute value of y. Okay, the reason being, if y were, let's say, negative 2, well, the fourth root of negative 2 squared, okay, would be the same thing as the fourth root of 16. The fourth root of 16 is equal to 2, but y was originally equal to negative 2. So that's why you have to put absolute value bars around that in order to get that to be equivalent. Okay, so absolute value bars in this case here. Let's look at number 10. Okay, for this one, we have the sixth root of 64 times x squared minus 3 all to the 18th. So I'm going to go ahead and split this one up into the sixth root of 64 times the sixth root of that quantity x squared minus 3 to the 18th power. Okay, the sixth root of 64 is just 2, because we know 2 to the 6th is 64, okay, from that index card you made of your perfect sixths. So that's just going to be plain old 2. You do not have to use absolute value bars when your radicand is simply a number. Okay, so 2 here is fine. But on this one here, we have a variable inside our radicand, and notice we have an even power, an even index, and an even power. So we have to watch out for absolute value bars. X squared minus 3 to the 18th is the same as x squared minus 3 cubed to the 6th power. Okay, so really this is the sixth root of x squared minus 3 cubed to the 6th. So x squared minus 3 to the 18th, when we take it the sixth root of it, we're just going to get this part here I have in red, x squared minus 3 cubed. So notice the resulting power is odd. Even, even, odd, that's when you have to use your absolute value bars. So we have absolute value of x squared minus 3 cubed, and then this 2 out here just gets brought down. So this here would be our answer. Let's look at number 11. we have the square root of 36, y to the 6th. So this one I'm going to split up into radical 36 times radical y to the 6th. Okay, the square root of 36 is simply 6. Here we have an even index. The index is 2, it's a square root. An even power, so even. The square root of y to the 6th would be y cubed. Your resulting power is odd, so you have to use your absolute value bars. This would be 6 times the absolute value of y cubed. Okay, finally, number 12. We have the fourth root of 16 times x minus 3 to the 24th. So we can make that the fourth root of 16 times the fourth root of x minus 3 to the 24th power. Fourth root of 16 is just 2, because 2 to the 4th is 16. X minus 3 to the 24th power, we can rewrite this as x minus 3 to the 6th power taken to the 4th power. Okay, 6 times 4 is 24, so it becomes the fourth root of x minus 3 to the 6th to the 4th. Okay, those 4s there, the 4 index and the 4 power, will cancel each other out, so you just get x minus 3 to the 6th power. Notice for this one here, I had originally an even index and even power, but my resulting power is also even. So in this case, I don't have to use the absolute value bars. It's still okay to use the absolute value bars. It's not going to hurt anything if you do, so if you want to be safe, you can just use them every time you have that even there, but it's unnecessary to use them here because that 6th power right there, that resulting power, is even. So really my answer to this one would just be 2 times the quantity x minus 3 to the 6th, or if you just want to make your life easier and be safe, you could also do 2 times the absolute value of quantity x minus 3 to the 6th. That would be okay as well. Alright, I know there was a lot in this one here, and I know this is slightly different from what we've been doing, so we're going to do a lot of practice on this next time I see you. Until then, have a nice day. You're all wonderful people. Be sure to shoot me an email with any questions you might have over this so I can know what to start with when I see you guys next time.